Hi, this is Pat, and in this topic, we're going to look at the Central Limit Theorem. Having just looked at the law of large numbers, you're going to see there's quite a relationship between the two. Oftentimes, people say they're the same thing. I look at them as the law of large numbers talks about how the means of the observations will begin to closely emulate the population means through many observations, and through more observations, they'll get closer and closer together. Here, I look at it as kind of absolutely the same, except it's based on the distribution or shape. So in other words, I'm looking at the normal distribution. The more observations, the more the normal distribution, or the bell curve, will begin to look like the population bell curve. So that said, let's do a little test around this, and you can get a little bit deeper into it as you go as well. I will be also publishing this in HTML, so you'll have all the code that I'm using. But basically, the code is pretty easy, pretty self-explanatory, but I'll just run through the highlights of it. First thing I start with is I variabilize the dice. So instead of just hard coding 6 die over 2 rolls or whatever, I say, or 6-sided dice over 2 rolls. I put in the number of sides because there are different dice out there for different games, different board games, etc. Some have 12 sides, some have 20. I even saw one online for 5. I think I saw one for 8. I mean, so there's all kinds of permeations of dice. So this way you can just change this variable if you want to. I'm going to stick with 6-sided and just 2 dice for the first roll, so we can talk a little bit about distributions as well. This distribution, when I ran it, it was 1,000,000, but I usually run it 100,000 times, 200,000, whatever it happens to be. The seed, of course, I use mostly for when we're in class, and we're looking at some code. I may say, let's all set a seed to a certain number to make sure we're getting the same distribution, then comment it out and sample away, just like we did before. Here, I created a function because I don't want to go through for loops, etc., and I want to keep the code very clean and simple and somewhat modular. So I created a function called multiple dice. So what I want to do with the dice is I want to pass in basically a sample. So I want to take a sample set each time, and I want to pass in 1 times the number of sides. So in this case, 1 to 6. So I want to see, it could roll any one of those on that particular dice. And then times our size is the number of dice. Here it is, times 2. And then replace is true. And I think the default is to replace. So that'd be one is once you roll it, put it back into the collection so it can run again. So the next time you roll, there'll be just as much chance of a 1 through 6 as the last roll at a 1 through 6. Then you're going to return the sum of dice. So basically here, if I rolled a 12, I'd return a 12. If I rolled a 7, return a 7, because I've only got six sides, 2 dice. I keep wanting to say that backwards, so I apologize. I have 6 sides and 2 dice, so I'm only going to get a 2 through a 12. So here in the frequency, what I want to do is I want to replicate. So instead of worrying about setting up a for loop, etc., it's much more efficient in R anyway to just replicate. And so when I replicate, I'm going to pass in the number of rolls. So in this case here, n is going to be the number of rolls. In our case, it'll be 1,000,000 or 100,000 on this particular case. And then with the expression to replicate, I pass in the function. So this is why I create a function. Just makes it very clean and very easy. Those values will be put in frequency of rolls. And then all I do is I change it to a table. That's just to make it easier to plot. There's really not much to it. So it's going to pass to a very large vector here. That vector will be then passed into the table. And of course, I'm going to factorize that because I'm not doing any math on those particular numbers. 2 through 12 represent rolls and basically factors. So I want to create that in a table. So it'll make it very easy to chart. I'm not using any fancy ggplot2 type charts or anything like that. But if you want to, that's fine. If you want to export the data and use whatever charting you want, feel free. But for this particular sample, I'm just using plot. And I'm passing in a few variables. The only thing I did extra is I passed in sipen equal 10. And what that does is it says, it tries to coach up R to not go too quickly to scientific notation in the numbers. That way I can actually see them printed out as they are. Because I think 100,000 or 1,000,000, it already starts doing an exponential or like scientific notation number, and that's just, I find, a little bit too busy, so I just want to put out the number itself. And you can see here I added a couple, titles, that type of thing. Some very light, I guess you call it formatting. Made the line red, made it a little bit darker so we could see it. Then I also want to pass in the frequency table. Add one extra line in the code that I didn't do here. I'll see if I'll remember to do that as well. But I'm also going to want to look at this particular number, 7. The reason being is when you roll 2 dice, 6 sides, and this will only apply for 2 dice, 6 sides, you are going to end up with 1 of every 6 should be a 7. So in other words, every time you toss it, 1 of every 6 or 6 of 36 should be a 7. So we're going to test that as well when we actually get to the code itself. So let's go run the code and have a look at it. And again, I'll have this published, and if you want to start with this and then make changes as you go, just highlight what's in the gray, copy it into R console, or yeah, you could actually copy it right into the console, or you can copy it into a script and recreate it from there, and then do what you want, modify it, make it a little bit nicer, whatever you choose to do. So now I'll come over, and this is the actual code exactly, and I'll show you what we're going to do with it. I'm just going to make sure I've got things commented out. I've got my seed commented out because I don't want to get the same answer each time, and I've got my cleanup commented out, which is fine. So now I can just select everything and go. Now, first time, what I'm going to do is I'm going to do multiples of 36, because like I said, I want to talk a little bit about this extra line I added at the bottom. I'm also going to print the rolls divided by the, it shouldn't be 11. I believe the table will be 6. I'll show you what I mean by that. We'll walk through it one time first to make sure I've got it right. So 6 sides, 2 dice, 36,000 rolls. So there you can see my values for my variables. Everything's fine there. Now I'm going to do the function. So now the function is set. All it's going to do is manage that. Now I'm going to do my rolls. There I have them. So you can see the values. So it'll be 2 through 12. So in frequency rolls, that's all I'm seeing is 5, 6, 10. Like you'd expect, shouldn't be anything less than 2, nothing more than 12. Now I'm going to pass them into a table. Makes it just easier to read. Then I'm going to come down here. I'm going to do my plot chart. So when I do my plot chart, there it is. I'm also now going to do my rolls table, and I'm going to stop there for a second because I need to check on something. So you can see here 7 occurred the most frequently, like you'd expect. Notice this distribution. This distribution, you can call it the beginnings of a bell curve, which it is, but it's actually what's called a binomial distribution because it's basically a triangle. And so I guess either one is fine, and it is kind of the beginnings of a bell structure, and we'll look at that in a minute, our normal curve, but our normal distribution, I should say. But it's actually called binomial distribution when it's peaked like this, and the reason being is there's only one number that can be, so there's not like a 7 and an 8 that could be the greatest amount of rolls. It's just going to be a 7. There's only one for each one beyond, and as you can see, so that's where it's called binomial. Now the first thing I'm going to do is I'm going to look down here. I'm going to look at this table, and I was messing with it for something else. So I got to make sure I got it right. So 2, 3, 4, 5, 7. Okay, so it is right. It is 6. So just to make sure that's correct, that number should be 5893. It is. So now I'm going to run this last one. And remember I said if you have a normal distribution and over a large amount of numbers, this should be very close to 6. Because what I'm doing for this last line of code is I'm saying give me the full amount of rolls divided by whatever resulted right here. 5893 results in 6.1, so that looks right. So this is really an example of law of large numbers. This is this particular number, because I just picked it out of the group. The reason why it's falling into place as it should is 1 of every 6 rolls should end up at around 6. That would be your best bet, or your best bet. Yeah, I guess we're talking about dice. So what I'll do now is we'll change some of these numbers and have a look. So let's see if I'll do another multiple of 36. We'll do 72,000, or we can do 720,000. That's fine. Control A. I'm going to run it. And it might take a little bit longer to run on that case, but it's still processing. Here we go. Oh, sorry, 720,000, so that's a little bit bigger. Of 2 die, 6 each, and notice here I'm getting very close in that law of large number piece as a review of the other. For 7, it's now 6.007 like we'd expect, but notice our binomial continues to be, as we'd expect, very, very uniform. So these numbers, just like you'd expect, this one, 6 and 8, are always going to be very close. So 99,004 compared to 100,090. And let me see, 5 and 9 will also be very close, 79, 94, 80. So you get the gist of that. So this is where a lot of observations across the dice will give you the same normal distribution, or the normal distribution will start meeting what you'd expect in the population distribution. Now what I'm going to do is change it up a little bit. I'm not going to worry so much about that last line because it's not going to make sense for this. And what we'll do is let's switch this over to 500,000. I think that runs fairly fast. Now I'm going to crank it up to 3 die. So now rolling 3 dice, what you're going to see is the distribution is not going to be binomial anymore. Give it a chance to process. There we go. Of that 500,000 observations across 3, notice now I'm starting to see that true bell curve, because now both 10 and 11, the odds of rolling 10 and 11 are about the same, and the odds of rolling 9 and 12 are about the same, but it's starting to see it's got a little bit more of a peak to it. The numbers are 3 to 18, or I guess you'd say less of a peak after a binomial. Sorry about that. Now what I can do here is crank it up. I'll actually say 5 dice and run it, and it should take a second or two to process those. And again, what I should see is 500,000 rolls across 5, and notice now you're starting to really see more of that normal distribution, or what we consider the traditional bell curve. So you can play with this. You can change the sides of the dice, you can change the number of dice and the rolls, but it'll start to really give you a good starting point for a explanatory sample of what central limit theorem is. And if you like, especially when you're with the 6-sided dice across 2, it's very easy for people to understand the 6 out of 36 chance of rolling a 7, or 1 in 6 I should say, and you can just add this little line of code to it, and it gives you a really nice way to explain both the central limit theorem and even the law of large numbers in the same example.